All right, guys, so this is now the last chapter, chapter number 12. We're going to now go into the learn about the property of gases. We're going to learn different gas laws. So I'm going to start first with the characteristics of gases, and I'm going to go through certain of these characteristics so that it gives you a little understanding, conceptual, of the behavior of the gases in regards to the certain laws that will be now explained in this chapter. And so the characteristics of the gases are as follow. Now, a sample of a gas assumes both the shape and volume of its container. Now, the characteristic number 2, gases are compressible. Characteristic number 3, the density of gases are much smaller than those of liquids and solids. And characteristics number 4, gases form homogeneous mixtures. Now the reason you observe that the gases are actually taking the shapes and the volume of the container, and also the gases are compressible, is because the gases they have large distances between the atoms or molecules of the gases, and therefore now these observations are made. What I'm going to go, guys, into the next is I'm going to talk about the gas pressure. And the way, guys, and also in units. And the way to understand the gas pressure is you can actually, in the macro world, what you can do is you can lean on the surface of your desk. And so you're going to create a pressure. So pressure is defined as force over area. And if you guys observe now, once you're leaning, once you put your hands over the surface of the area and you lean your weight against those both hands, you're pretty much applying pressure or force over the area, and the area, of course, will be whatever the area covered by your hands. So the gas molecules do the same thing pretty much. They're tiny, small, but when they, for example, you got the surface of let's say of a certain liquid, and so the way the pressure of the gas now acts on the surface of the liquid is that they exert now a force over the area by just moving and hitting, guys, the surface of the area of the liquid, for example. And so by doing so, they exert a force due to the, I guess, movement and the weight of the gas molecule. And because they have a small but certain area associated with these atoms and molecules, they do have some little tiny surface and areas. And so what they do is when they hit the surface now of the liquid, because so many of them, they now exert that force that they possess over the surface now of the entire liquid here. And so the pressure is defined as the force over area. Now, so what are the units now of pressure? The units of pressure is Pascal, but how's it derived? Well, the force is nothing else as the Newton, and the area is meters squared. Now, the Newton now can be broken down to the kilogram times meters over second squared, and also the meter square will stay now. And so when you now do the mathematics here, you will be dividing now by meter square. But remember, guys, when you divide, what happens is you flip now this second term, guys, in the division, right? And so you're going to do the reciprocal, you're going to do 1 over m squared. So let me just do it now. So I'm going to do now multiplication here, and I'm going to flip that 1. I'm going to flip now meter squared, and I'm going to put 1 over meter squared. Now, this and this will cancel. Now you will have m in here. And so what you're going to get here, kilogram per meter times second square. And that's what the unit of Pascal is, and also the unit of pressure. So again, after I do all of these, now I'm going to reduce now this by the m, and also this by the m. So this will result now kilogram over meter times second square. and that will be the unit of Pascal in here. And that's the SI unit, guys, of pressure, okay? So this is what the Pascal is. Now, how do you calculate the atmospheric pressure? All right, so let me just clear all this. And what you need to realize is that the way you calculate, let's say this is the Earth, this is the surface of the Earth, and there's some, let's say, part of the ocean or sea level. So you have to now build a column that is coming, that is has 1 centimeter now, 1 centimeter length, 1 centimeter width, and it now being extended all the way out into the space where there is now vacuum begins. This column of air. Let me just do a little correction here, and let me do just a little better drawing here so that you can guys see now the column, like this phantom column of air. But this is how we calculate, guys, atmospheric pressure in a nutshell. Just explaining. So this is the column, let's say, of air. This has to be, of course, all straight. And so when you do this column, you have 1 centimeter, 1 centimeter width and length. And so this, again, column contains the air molecules now inside. And again, it's on the sea level. It'll go all the way through the atmosphere to the level where you now have you reach the vacuum, no more air molecules. And so now we can calculate the atmospheric pressure. And so what you have to be, guys, cognizant of the fact here that this column of air has a certain mass to it. And the mass, guys, of this column of air is 1 kilogram, 1 kilogram here. So how do you calculate now the pressure that this air exerts on the surface of 1 centimeter square? And so the way we're going to do it now is that we're going to do 1 kilogram times, in other words, it's going to be force over meter squared. That's what we need to do because that's what the pressure is. Now, the first force here is nothing else as the weight of the air. And the weight of the air, guys, is nothing else as the mass times the G, which is F here of air is mass of the air, which is 1 kilogram times the acceleration due to gravity, 9.80 meters per second square. So that will be the calculation of force that the air exerts on this surface here. And all we have to do now with the centimeter square, convert, guys, into the meter square. And that's what I'm going to do in a moment. So I'm going to do P atmospheric pressure will be now kilogram times 9.80 meter over second squared, now divided here by centimeter square. However, remember, guys, we need meters here because force in itself has also the units of meter. We need to match, guys, the units in order to have, guys, apples and apples here. Now, how do we do this? So you know that 1 centimeter, or let's say 1 meter, actually a better way to convert now, in my opinion, 1 meter contains 100 centimeters. And then when you square now 1 meter, you're going to square also 100 centimeter, so that algebraically the both sides still equal to the same thing. So now you're going to say 1 meter square is nothing else as the 1/10 to the positive 4th centimeter square. So now I can do the conversion here real quick. I'm going to say that 1/10 to the positive 4 centimeter squared, cancel, is equal to 1 meter squared. And that's where you guys now got the units of, correct units of pressure here, which will be Pascal, because you'll remember, guys, I just did handling this kilogram times meter square divided by the second square divided by the meter square, guys. Remember, it's a Pascal unit. So now, when you do all of these calculations, guys, what you're gonna get here is 1, because it's one significant figure here, 10 to the positive 5 Pascal, and that would be your atmospheric pressure here. And this is the way, guys, to understand what the atmospheric pressure is. Okay, now, but how do we actually measure the atmospheric pressure? Now, the way we measure, of course, we're not going to construct the column that goes from the surface of the Earth at the sea level and goes all the way to the vacuum. So instead, we're using actually, instead of the air in here column, we're using a column of mercury. So let me now get to this now column of mercury and explain you guys what a barometer is all about and how we use barometer to measure the atmospheric pressure. So a barometer. Now barometer. So what the barometer does is an instrument used to measure atmospheric pressure. It consists of a long glass tube. And so the way they construct it is, let's say you have this dish in here filled with mercury. Let me just make this dish here. So it's made with, filled with mercury, of course. And then you have, let me just move this a little bit up so that's not on the way here. Barometer. And so you got this, again, dish filled with mercury here. It's all filled, guys, with mercury inside. Ag, that's abbreviation for mercury element, for mercury metal. Now, so you fill first this glass tube that is sealed on one end, and you fill it all the way up, all the way up. Let's say you have this tube of mercury. Oops, that doesn't look right. You got this tube of mercury with this one end close, and you filled this with mercury all the way up to the rims, all the way up, all the way up. Everything is filled with mercury here. And what you do next is that you are now moving this, and you, inside of this dish, you now invert this column of mercury. And what you're gonna observe here, guys, now this mercury here will now flow down a little bit, and will now stop at certain point. This is the mercury meniscus here, okay? And it will stop at certain point, Ag. And the reason it will stop, guys, the reason it will stop is because now the air molecule will be now exerting the pressure on the surface of this mercury here that is in the dish. And so with these now air molecules, by supplying that force over area pressure, they will be able to hold now the column of this mercury metal that we will now measure. And that's what gives us, guys, now the what's called the atmospheric pressure. So we're going to put a ruler here. We're going to put from the surface of this mercury here. We're going to put a ruler here. And what we're going to do now here, this meniscus here, the meniscus here, we're going to read now the millimeters of mercury. Let's say this is my 760 millimeters of mercury, and the 760 millimeters of mercury is called the standard atmospheric pressure. Now, what is 1 atmosphere also equals to 1 atmosphere, and was originally defined as the pressure that would be support a column of mercury exactly 760 millimeters at 0 degrees Celsius at a sea level. Okay, now this also 1 atmosphere, again, let me just write down, is 760 millimeters of mercury, and also it's equal to 760 now torr, units of torr, after the famous Italian scientist. In Italian, it would probably sounds like Torricelli. In English, we call it Torricelli. So whatever guys the way you want to name it, call it, that's fine. So now this 760 torr will be equal to 760 millimeters of mercury, and that's exactly how you guys are going to do it with the actually putting the ruler right against that column of mercury, and just measure the mercury height. And so the pressure, atmospheric pressure that is being exerted by the molecules of air will be now supporting this column of mercury here. And so let's say if you take now this assembly now higher in elevation, you will have now thinner air and less molecules of air now I guess, bumping or uh, bouncing off the surface of this mercury in the dish here, and as a result, the atmosphere now, atmospheric pressure will be lower, and therefore less force now to support the column, this weight of the mercury here. That means that the mercury now will flow now more down, and then you guys are gonna read now the lower millimeters of mercury here, and that will indicate, guys, the lower the atmospheric pressure. So that's how it works, guys, measuring the pressure with the column of mercury here. Now, what I also, guys, want to mention here, because I also want to cover here in this part of the video a manometer. I also want to measure, guys, define the pressure in terms of the height of the column of a substance times the density of it times the g, which is the acceleration now due to gravity, 9.80 meter per second square. Now, if you guys, kind of like doubting the validity of this formula, remember, guys, very important thing here in chemistry and physics is that you can always confirm the validity of any formula by actually plugging in the units in here and see if you're actually recovering now Pascal in here if you do the combination of these terms multiply by each other. All right, let's do it. Let's verify if now this is actually the height of the column times the density times the G will actually produce, guys, the units of Pascal. And that's pretty much, I'm going to validate that that's the same thing as force over area. Now, the height, of course, we can measure in millimeters of mercury, but we also can convert it into the meters. Now, the density could be measured in kilogram per meter cube, right? Because the density is measured mass over volume, and these are SI units here I'm using, times now, again, meter per second square, that's the acceleration due to gravity. Let's see now if we're gonna get now 1 kilogram over meter times second square, which is nothing else as a 1 Pascal, right? So let's see if we get that now. All right, let's do it. Or Newton per meter square. Let's see if we get that. So we definitely can do now this, and in the bottom we got meters here, because meter squared divided by m to the cube is giving us meter. And so what we wind up now with the unit is kilogram over meter times second square, which is nothing else, guys, is what? I just match my unit of Pascal. So this formula, guys, is, I'm kind of proving it's correct. And again, the units always, guys, giving you the, if you, for example, in doubts how to set up a certain problem, and if the formula correct or not, you pretty much put the formula, plug the numbers in with the units, and if the units come out on the other side correct, that are absolutely properly describing the term, in this case pressure, that means your formula is correct. Now, it's one of the ways to validate your, I guess, your formulas. Now, so this was, guys, a barometer. That's when you try to measure the atmospheric pressure. But how do you measure the pressure of the gas that is captured, let's say, in the cylinder that is less than atmospheric pressure? For example, some of the gases exert the pressure less than atmospheric pressure, or the gas that actually exerts the pressure that is higher than atmospheric pressure in some kind of cylinder. And the way we, guys, do it now, is by using what's called a manometer. Now, let me just state here what it's called, a manometer, and I'm going to explain what it is in a moment. Manometer. And so the manometer is a device used to measure pressures other than atmospheric pressure. And this is just I mentioned. So how do they do this? Well, first of all, we need to now put this formula here. P is equal to H times D times G here, because this formula will be now instrumental here to now help us to figure it out now the pressure of that gas that is now captured in the cylinder, some kind of container. All right, let's do it. So let's say I have this primitive manometer here that has this this container. You have a gas in this container, some gas molecules here, and then you got now here it's connected now to this tubing here. It's connected now to this tubing here. You got this valve in here, let's say that you can open or close. And this one is now can be open to the atmosphere. And so the next thing that you got this U-shaped U-shaped here, made of glass, kind of column looking here. And so this now is filled with mercury. You got, for example, something looking like this. So this is now mercury, guys, filling this. And by the way, the first thing I will do, I will actually seal this one here. It will be sealed. This is sealed. This is sealed. And so what happens here now, I got this mercury level here, going all the way up here, this meniscus of the, and so here you got vacuum, let's say, vacuum here. Vacuum here. Now, so, and then you got the gas, of course, now occupying this, the empty space here, and then it hits now the mercury here also, the surface of the mercury, and of course it exerts, guys, a certain pressure here because these molecules or atoms of the gases now start bouncing off the surface of this mercury on this side here, and as a result, there is a pressure now or force of area exerted now on the surface of this mercury here, and as a result now, this pressure of the gas is actually supporting now so much of mercury now here. And remember, guys, this formula now is very instrumental, guys. So now what's the now pressure of this gas that is captured inside of this container? And that pressure will be nothing as the P sub H. In other words, as long as I measure now the height of the column, and I'm going to now multiply now this height by the density of mercury times the G, which is 9.8 meter per second square, I would get now my pressure in units of Pascal, or you have another option that can express now this pressure in units of millimeters of mercury. So that also would do it, guys. So in other words, there's vacuum here, so there is no of any kind of air molecules or any other gases that are bouncing off now the surface of this side here. So the pressure of the gas is just purely the is holding now the weight of this particular now column of mercury. And so that would be the measurement now. This is how the manometer now measures the pressure of the gas that have been captured, guys, by the in some kind of cylinder, and the pressure here is obviously below the atmospheric pressure here. Oops, below, I should remove that E, below the atmospheric pressure, Okay, what if your gas captured actually is higher than the atmospheric pressure? So you will construct, guys, you will use a very similar manometer here, very similar here. And again, this tubing will be now controlled by the valve, opening or closing here. Okay. And so again, U-shaped tubing here. But in this case now, what we're gonna do here, we're gonna open now this tube here. You see this was sealed here, vacuum here, no air, nothing in here. Just empty space, everything evacuated there. But here now, what you guys are gonna have some gas captured, right? Some gas captured. Let's say you got your mercury level right here, a little concave shape. And this now, let's say here, your mercury now on this side now, at this level here. Now, and so you got this gas captured now inside here. And of course, the gas, of course, is producing some pressure here by bouncing off the surface of this side of the mercury column now. Mercury, I would say, the side of the U-shaped, I guess, this glass of mercury here. And what's now the difference between this and this is that you got now, it's exposed to the air in here. And so what you guys now have to be cognizant of this, cognizant is that there is a air pressure now that is being bouncing off now this side of the mercury. So when you try to now figure out the pressure of the gas that has been captured now here in this manometer, that it would be not only now the, by the way, this is a P sub H, not only the P sub H in here, right? But also, guys, also P atmospheric. And this gas now, you know, has much higher pressure than this gas, because not only that is supports the height of this column of mercury, a weight of this mercury with the such column, right? But also on top of it, it also, guys, supports now this gas, also whatever the column of air that is now it's bouncing, so this air molecules now bouncing off the surface of this mercury metal here. And remember, guys, I showed you in the beginning of the explanation here, if you put this manometer at the sea level, that will be your very the same column of air that goes from the sea level all the way to the vacuum through the atmosphere. So that will be your atmospheric pressure here, and that's exactly what I just put here. So the P of the gas here will be now having a high pressure, because not only it's going to be P sub H, but it's also, guys, you have to include P atmospheric. So again, this pressure of the gas is lower than atmospheric pressure we measure with this manometer here. This now gas is much higher than the atmospheric pressure. And so the manometer, of course, again, guys, is a device used to measure pressure other than atmospheric pressure, meaning either below the atmospheric pressure or higher than atmospheric pressure. Okay, so see you guys in the next videos. I'm going to now go into the gas laws, but actually before I do so, I'm going to do some conversions of, because the gas units could be of different types. So I'm going to do, guys, conversion of certain units of gas from one system to the other system. We're using now different units of gas pressures. So I will, guys, go and do some problem solving. And if you guys still have any questions, you can always ask me during our live Zoom sessions. All right, so I'll see you guys in the next video.